One of the most useful general applications of the derivative was that the derivative of a function gave you a sense of the function's rate of change. For example, the derivative of position was velocity, because the velocity represents the rate at which the position is changing over time. So, what does the antiderivative represent? Well, we've seen a couple of different applications of it, but for the most part, we have been focusing on the use of the antiderivative to find the net area under a curve. Today, we're going to think about that in a slightly different way. Not the net area under a curve, but the net change in the amount of a quantity over time. So suppose that we have a function lowercase f of t, and this function represents how fast a quantity is changing, the rate. The question is, if you know how fast the quantity is changing, can you figure out how much the quantity changed in total from one start time to a finish time? And the answer is yes. If you want the net change in the amount that you have from starting time A to final time B, then you can just take the definite integral from A to B of f of t with respect to time, and that will be the net change in the amount of the function. So let us rephrase that. If you want the quantity at time B, and you know the quantity at time A, you can just add the net change to find the new amount that you have at some later time. Let's apply that principle to the following example. Suppose that at time t equals 0, the radius of a ball is given by r of 0 equals 2. The radius is changing over time at a rate of sine 2 pi t. So find the radius of the ball at time t equals 1. So what we are looking for is the radius of the ball at time 1. And what we know is the radius of the ball at time 0. And we also know the rate of change of radius at any given time. So if we take the initial radius, and we take the rate of change, and we integrate the rate from start to finish, and we add those numbers together, then we'll get the radius at the final time. Now we are told that the radius of time 0 is 2. And we can find the antiderivative of sine. The antiderivative of sine is minus cosine, and then to counteract the 2 pi that would appear from chain rule, we can divide by 2 pi. Now, taking the integral from 1 to 0, let's see what happened. 2 plus, plug in 1 for cosine. Cosine of 2 pi is 1. Then let's subtract what we get when we plug in 0 for cosine. But cosine of 0 is equal to 1 as well, and so we have negative 1 over 2 pi, take away negative 1 over 2 pi, and the result is 2 again. So what's happening with this ball that it is exactly the same radius at the end of the time period as in the beginning? Now here is the graph of the rate of change. The rate of change sine 2 pi t over the interval from 0 to 1. When the rate of change is positive, the radius is increasing. We're accumulating more and more radius. But when the rate of change is negative, the radius is decreasing and we're losing radius over time. But because of the symmetry of sine t, because of this positive portion is equal in size to this negative portion, the radius went up a bit, but then went right back down to its initial value at time t equals 1. And so, although the radius changed significantly, rising and falling over the course of this time interval, its final value was the same as what it started.